Welcome back everyone to this lecture on gradient descent and backpropagation. If you've dabbled in machine learning before, or if you've even looked at some online articles, you've probably already heard of the term gradient descent. Let's quickly go over it with a high-level overview and then discuss backpropagation. Gradient descent is an optimization algorithm for finding the minimum of a function, which is useful to us because we want to minimize that cost function. So to find the local minimum, we take steps proportional to the negative of the gradient. Let's go ahead and go through a very simple example in just one dimension. So basically what we have here is our cost on the y-axis, so the result of that cost function, and then on the x-axis we have a particular weight that we're trying to choose. So remember, we end up choosing a random weight in the beginning. So let's say that blue point initiates that random weight that we chose. And we want to somehow choose a weight that's going to minimize that cost. And we can see here just visually in one dimension, that's basically at the bottom of that parabola. So the way gradient descent works, in just a high-level overview, is that you end up taking the gradient, which we know is the derivative of the function at that point, and then seeing which way it goes in the negative direction. And then we end up taking step by step a descent along that gradient until we finally see that we get that minimum in our cost. So we see here just visually what the parameter value to choose to minimize our cost is. So finding this minimum is really simple for one dimension, but our cases we're going to have a lot more parameters, so we're not going to be able to do that visually or with such a simple diagram, meaning we're going to need to use built-in linear algebra libraries that our deep learning library will provide. Using gradient descent, we can figure out the best parameters for minimizing our cost. So for example, finding the best values for the weights of the neuron inputs. And we're going to go a lot more into the mathematics behind gradient descent when we actually go through the math example. So now we just have one issue to solve, and that is how can we quickly adjust the optimal parameters or weights across our entire network. In that one example we just showed for a single weight. But what if we want to actually go and then fix all the weights or adjust all the weights for the entire network? And that's where backpropagation comes in. Basically, backpropagation is used to calculate the error contribution of each neuron after a batch of data is processed. And it relies heavily on the chain rule from calculus to go back through the network and calculate these errors. And the way backpropagation works is just it calculates the error at the output and then distributes back through the network layers. And it requires a known desired output for each input value. And remember, that's supervised learning. We need some sort of comparison to actually get that error. So the implementation of backpropagation is going to be further clarified when we dive into the math example because it really relies heavily on the chain rule and derivatives, and it's not something that really works with slides. So instead, we'll kind of show you by hand how this entire process works. But now that we've finished off our very high-level overview of the theory behind neural networks, let's go ahead and get a quick discussion of TensorFlow's Playground, which is a really fun website that allows you to kind of visually see a lot of the aspects we've been talking about through the previous lectures. Thanks everyone, and I'll see you at the next lecture.